Let's look at the solution to another AP Calculus free response question. This problem happens to include concepts from units 2, 5, and 6. As you can see, we have a graph here, and then we're going to answer some questions about the graph. The graph of the function f, consisting of 3 line segments and a quarter circle, is shown above. Let g be the function defined by g of x equals the integral from 1 to x of f of t dt. So that's the setup. G is an accumulation function based on this graph, and then we're going to answer 4 questions about function g. We'll start a new slide and we'll attack letter A. Letter A says to find the average rate of change of g from x equals -5 to x equals 5. Let's just make a note right now that g of x is the definite integral from 1 to x of f of t dt. I'm just writing that out a little bigger so we can see that. And we need to find the average rate of change. Let me write that like this. For g, so we're going to do g of b, which is 5, minus g of a, which is -5, over b minus a. That's the calculation for doing the average rate of change. It's the old slope formula from Algebra 1 class. And in order to compute this average rate of change, we're going to need to have values for g of 5 and g of -5. So let's take a moment and we'll go ahead and compute those separately just to stay organized. G of 5, we can find that by computing this definite integral. Right? We stick 5 where x is. And we're going to basically use area to figure this out. So we're going to have, let me use a little bit of color over here. For g of 5, we're going to start at 1, and we're going to go all the way out to 5, which is out here, and we're going to compute the area under the curve. So we've got 2 geometric shapes to compute, this triangle and this rectangle. The triangle is 2 on the bottom and 4 on the height. So that's 2 times 4 is 8. Half of that is 4. So that area is 4 for the triangle. And then the rectangle is 2 by 4, so that's 8. And so, what is that? That's 12, right? So g of 5 is 12. And we just use area to do that. Okay, let's compute g of -5. We're going to do something very similar. When you write the definite integral, it looks funny because the limits of integration are out of order. So usually what we'll do is we'll set those right by sticking a negative sign in front of the definite integral and then swapping the limits of integration. Okay. Again, we need to use area. So remember, we're doing the opposite of the area from -5 to 1. So I'm going to put a big negative sign right here, right now, and then I'm going to go compute these areas. From -5 over to 1, it's this section of the graph here. So we have a triangle, we have a quarter circle, and then we have another triangle. Now remember, these areas are below the x-axis, so they are negative. So that first triangle is going to be a negative, and then what is it? It's 1, 2, 3 by 4, that's 12. 12 over 2 is 6, so that's -6. The semicircle, the quarter circle, is going to be, that's pi r squared over 4. The radius is 2, so that's 4 pi over 4, so that's pi. That's -pi. And then the triangle is a 1 by 2, which is 2 over 2, which is 1, so -1. So this whole thing is going to be what? -7 minus pi, but we're doing the opposite of that because of the negative sign out front. So this is 7 plus pi. So we have these 2 function values. I'm just going to highlight them. I'll put them in green. They're not final answers, but they are 2 values that are important for us to get the final answer. And now we'll go back and we'll compute that average rate of change as soon as I get my pen back on. Okay, so that average rate of change is g of 5, which is 12, minus g of negative 5, which is 7, plus pi, over 5 minus negative 5. The denominator, I hope you can see that's a 10. And then if we simplify the numerator, we're going to have 12 minus 7, which is 5, and then minus pi. And that's about as good as it's going to get for that value. So we're going to call it quits there. We'll highlight this thing. That is the average rate of change over the interval negative 5 to 5 for function g. Okay, we had some accumulation there, and we had some good old-fashioned rates of change. All right, we'll attack letter B on the next slide. Letter B says find the instantaneous rate of change of g at x equals 3, or state that it doesn't exist. In the last problem, we did the average rate of change, which is the old slope formula. Instantaneous rate of change, we're going to use derivatives. Let me remind you again that, that I keep forgetting to hit my pencil, that g of x is defined by the definite integral of f of t. Okay. To find the instantaneous rate of change at x equals 3, we just have to do the derivative. So first, let's write down the formula for the derivative of g. We're going to use the fundamental theorem of calculus, that first part of the fundamental theorem. And remember, basically, the trick is the derivative is just going to be taking this thing and sticking it where the t is. And so we just get f of x. There's no chain rule involved here because it's just the variable x, not a function of x up there on the top limit of integration. So the derivative of g is just f. That means if we want to know the instantaneous rate of change of g at 3, we just plug 3 into f, and we get that right off the graph. So I'm going to go over to the graph, and I'm going to go out here to 3. There's x equals 3. The y value is 1, 2, 3, 4, and we're done. The average rate of change, the instantaneous rate of change. Come on, man, you got to say that right. The instantaneous rate of change for function g at x equals 3 is 4. If I'm taking the AP test, I would probably write that sentence out. But you don't need to sit here and watch me painstakingly write on this iPad. So the instantaneous rate of change for function g with respect to x at x equals 3 is 4. Okay, we'll attack letter C on the next slide. Letter C asks, on what intervals, if any, is the graph of g concave up? And we're going to justify our answer. So let me remind you about a couple things. The way we'll know that g is concave up, after I fix my pen again, we'll know g is concave up if g double prime is positive. So we want to look for where that's going to happen. Remember, we said g prime of x equals f of x. That means g double prime of x is the derivative of f. So we really want to know where f prime of x is positive. And for that, we look at the slope of the graph. So notice, on this graph, there are two intervals where f has a positive slope. So we'll say g is concave up on, what is that, -5 to -2. And 0, 2, 1, 2, 3. And that's because the slope of the graph is positive. In other words, the second derivative of g is positive. All right, that wasn't bad either. I like those kinds of problems. So these are the two intervals, right? -5 to 2 and 0 to 3. And I indicated those. I need a thicker highlighter so it doesn't take me so long to highlight these things. It's these two parts of the graph right here where this thing slopes up. Okay, that's it for letter C. Let's take a look at letter D on the last slide, and then we'll be done with this video. Letter D asks, find all values of x in the interval from -5 to 5 at which g has a critical point. Classify each critical point as the location of a local maximum, local minimum, or neither. And then we'll justify our answers. So we got to find the critical points, and then if we have any local maximums or local minimums, we'll make sure we indicate that. So I'm just going to get organized. Let's jot down this interval here. We're talking about x from -5 to 5. It's an open interval from -5 to 5. We need to find critical points. And we want critical points of the function g, right? And we already know that g prime of x equals f of x. All right? So we need critical points of g, meaning we're going to set f of x equal to 0. So we just need to find out where f of x equals 0. We'll go to the graph. So we have a 0 here at, what is that, -2? And we have a 0 at 1. So from that graph, we just discovered that we have critical points at x equals -2 and x equals 1. They're critical for the function g. So what we usually do is we make a sign diagram, right? Put -2 there, put 1 there. And we're going to analyze g prime on this sign diagram, which really means we're going to analyze f. So to the left of -2, what is the sign of function f? Well, notice f is down here below the x-axis, so f is negative. That means that g prime is decreasing on that interval. To the right of -2, this little semicircle here, or that's a quarter circle, we're also below the x-axis. In fact, we're below the x-axis on this piece of that line segment as well. So between -2 and 1, we're always below the x-axis. So that's also decreasing. So right now I can see that this is a neither. It's neither a max nor a min. But notice that on the right side of 1, the function is positive. That means that g prime is positive, so it's increasing. When we change from decreasing to increasing, we get a minimum, local minimum. So this sign diagram basically tells us that x equals -2 is critical, but neither a max nor a min. And x equals 1 is critical, and a local minimum of f. Excuse me, of g. So this is, oops, excuse me. Essentially what we want to know is, do we have any extreme values? So we do have a local minimum at x equals 1 on the open interval from -5 to 5. There's another critical point at x equals 2, but it's neither a max nor a min. Okay, I think we did it. So that wraps up this free response question. Good luck with your studies. If you need me, you know where to find me. Take care.